We are now going to discuss linear maps between vector spaces, their basic definitions. First, we want to understand what is a linear map, and we're going to introduce it using first examples. In the first example, we're going to assume that we have a number, a that's a real number, and we're going to define a function or a map from R to R such that f of x is equal to this number a multiplied by x. The property of this function is as follows. If I picked two numbers in R, and if I picked another two numbers in R, alpha and beta in R, I have the following. F, the function of alpha u plus beta b. I'm going to substitute alpha u plus beta v instead of x. And so since f of x is equal to a multiplied by x, then f of alpha u plus beta b is equal to a multiplied by alpha u plus beta v. So rearranging, this is equal to alpha au plus beta av, which is equal to alpha f of u plus beta f of v. So because this function has this form, f of x is equal to a of x, I'm able to say that f of alpha u plus beta v is equal to alpha f of u plus beta f of v. This would not have been possible in other examples. This is not possible. For f of x, for example, equal x squared. In this case, f of alpha u plus beta v is not going to be equal to alpha f of u plus beta f of v. Okay, let's look at another example. In this new example, we have a1 and a2 real numbers, and now I have a function f that's from a two-dimensional vector space to the real numbers. So for every vector in R2, and this vector has two components x1 and x2, the function is equal to this first number a1 multiplied by the first component of the vector plus a2 multiplied by the second component of the vector. So f takes a vector and gives me a real number, and this real number is equal to a1 x1 plus a2 x2. Now let's see if it abides by the same property. If I pick two vectors in R2, and if I pick two numbers in R, alpha and beta, I have f of alpha u plus beta v. I'm going to substitute alpha u plus beta v instead of x in the function, and u and v are vectors, so u has components u1 and u2, and v has components v1 and v2. So this is equal to a1 multiplied by the first component of the vector, and the first component of this vector is equal to alpha u1 plus beta v1 plus a2 multiplied by the second component, which is alpha u2 plus beta v2. Again, by rearranging, you will find that because of the form of this function, I can say that's equal to alpha f of u plus beta f of v. And this particular function can be written in matrix form as follows. F of x is equal to a1, a2 in this matrix form multiplied by x1, x2. And so you can use this, the row multiplied by the column. So this row multiplied by the column multiplication operation to write this function. The same applies for even functions that are from R2 to R2. But for this function, I'm going to have four different real numbers, a11, a12, a21, a22, and I'm going to say that any vector in R2, of course x has two components x1 and x2, the function of x takes this vector x and gives me another vector with two components. These two components are function of the old components x1 and x2. These functions are linear, and the coefficients are equal to these constants a11, a12, a21, a22. And again, if you pick u and v in R2 and pick any alpha beta in R, then you have f of alpha u plus beta v is equal to alpha f of u plus beta f of v. And you can also write this function in this form. F of x is equal to this matrix of constants a11, a12, a21, a22 multiplied by the vector x. And again, using this row multiplied by the column convention, you get a11 x1 plus a12 x2, which is the first component of the resulting vector, and then the second component is the second row multiplied by this column, a21 x1 plus a22 x2. And so in short, a linear map is defined as follows. A linear map between two vector spaces v and w is a function from v to w such that for any two vectors in v, I'm going to call them u, v, small u and v in the vector space v, and for every two numbers alpha and beta in R, t of alpha u plus beta v is equal to alpha t of u plus beta t of v. So this is the definition of a linear map. And matrices are in fact simply just linear maps. For the study of linear maps, we need to study a special type of sets. These are called the kernels of linear maps. The kernels of linear maps are the sets of vectors which the linear map maps to 0. So the basic definition is as follows. If I have a linear map between the two vector spaces v and w, the kernel of t, or written as kernel of t, ker t, is the set of all vectors that are mapped into the 0 vector. So ker t is the vectors in v, they're the vectors in the linear vector space v, which when t is operated on them gives me 0. So let's look at an example. So I have a linear map that takes a vector in R2 and gives me a real number. And the form of the function is such that for every x in R2, x has components x1 and x2, f of x is equal to x1 plus 2x2. So as you can see, the function is a function of the two components of the vector x1 and x2, and it gives me just one value, which is x1 plus 2x2. And the question is, what are the vectors that are mapped to 0? What's the kernel of this map? So in order to find the kernel of the map, I'm going to take the function f of x, x1 plus 2x2. I'm going to say it's equal to 0. And when I set it is equal to 0, I realize that the vector that can map to 0 is the vector whose component x1 is equal to negative 2x2. So any vector whose component x1 is equal to negative 2x2 is mapped to 0. So if I set, for example, x2 is equal to alpha, any real number, then x1 is equal to negative 2 alpha. And so the kernel of f, which are all the vectors that are mapped to 0, are the vector that has to component negative 2 alpha and alpha. Any linear map between a vector space Rn and a vector space Rm has a matrix representation. It has an m by n matrix representation that depends on the choice of the coordinate system. So after I choose a certain coordinate system for Rn and a certain coordinate system for Rm, T, which is a linear map, has an m by n matrix representation. As you can see, T operates on vectors in Rn. So this vector has n components, and because it has n components, T, the matrix, has n columns. And so when you do the matrix multiplication, you take that row and you multiply it by that column. And so the number of columns here have to be equal to the number of components of that vector. And that's why the matrix has n columns. It also has m rows because the resulting vector, I'm going to call it y, is y1, y2, up to ym. The resulting vector has m components, and so because it has m components, the matrix has m rows. As we showed in the previous slide, any linear map between vector spaces has a matrix representation, and this matrix representation depends, of course, on the coordinate system. So what happens when I change the basis of that coordinate system? So what happens to the components of T? So let's look at a linear map T from Rn to Rn, and let Tij be the components of the matrix representation of T. when B is equal to E1, E2, and so on, En, is chosen as the coordinate system. Now, what are the components? T prime ij, when B prime, E prime 1, E prime 2, and so on, E prime n, is chosen as the coordinate system. So let's look at the figure here. We studied before that if I have E1 and E2 and a vector U in a coordinate system, and if I have a new coordinate system E prime 1 and E prime 2, then the coordinate transformation matrix Q is made out of the components E dot prime 1 dot E1, E prime 1 dot E2, E prime 2 dot E1, E prime 2 dot E2. And in the new coordinate system, E prime 1, E prime 2, U, it's actually the same vector, same direction and everything, but the components of U prime are actually equal to this Q multiplied by U. Now, what happens if I actually have a matrix? So a matrix, as we said, is a linear map. So if I have a matrix M, then the function of M is that it takes vectors U and gives me a new vector V. So if I have here V, it's the result of multiplying the matrix M by U. So in the new coordinate system, now I have V prime, which is equal to M prime multiplied by U prime. And so what I'm looking for is actually, if I know the components of M, what are the components of M prime knowing Q? So we're going to do this using what we studied before in the coordinate transformation. First, I know from the previous, from studying the change of basis, when we studied linear vector spaces, I know that U prime is equal to Q multiplied by U. I also know that V prime is equal to T prime U prime, and instead of using M prime U prime, I'm actually just using here T prime U prime, and V is actually equal to T U. And so V prime is equal to T prime U prime, which is equal to T prime Q U. I also know that V prime, the components of V, is equal to this matrix coordinate transformation multiplied by V. And so V prime is equal to QV, and V, as I know, is equal to TU. Again, I'm just going to correct the terminology that I'm using here. This is T prime U prime, and this is equal to TU. And so I have here QTU. And so now, because these two are equal, I can take this and equate it to this. Therefore, I have T prime QU is equal to QTU. Now this is true for any vector U, and so I can just say that this matrix T prime Q is equal to QT. So T prime Q is equal to T. Now Q is an orthogonal matrix. Its inverse is Q transpose, and so if I multiply by Q transpose on both sides here, I get that T prime is equal to QT Q transpose. And so this is the relationship that I'm looking for. So the relationship between the vector and the components of the new vector after coordinate transformation, U prime is equal to QU. And the relationship between the matrix, here I'm going to call it TU, and here I'm calling it T prime U prime. The relationship between the matrices after coordinate transformation is that T prime is equal to QT Q transpose. On the website, you have a tool. You can input the 4 components of the matrix, the 2 components of a vector, the angle of rotation of a coordinate system in degrees, and then the tool will give you the coordinate transformation matrix, the new vector U prime, and the new matrix M prime after multiplying Q transpose. So you should do this by hand, and you should do it using the tool and compare and see if you're getting exactly what the tool is predicting or not. So what does it mean that I multiply 2 matrices by each other? So let's look at what a matrix does. So a matrix basically takes vectors, let's say from Rn, a vector U, a vector M, and gives you a matrix Mu in Rn. So M, let's say, is from Rn, to Rn. And let's say I have another matrix, n, also from Rn to Rn, that takes vectors, takes this vector, and gives me another vector here, n, m, u. The matrix nm, when I multiply the matrix m by the matrix n, I actually get this nm multiplied by u, which is a linear map from, and this matrix nm can be found by multiplying the rows of n by the columns of m. And so this gives me the map that corresponds to first multiplying by m and then second multiplying by n. Now let's try to understand when is a matrix invertible and when it's not. So let's start looking at examples. So the matrix whose components are m11 is 1, m12 is 2, m21 is 2, and m22 is 1. Basically it looks like this, 1, 2, 2, 1. Let's look at its function. Its function is it takes the vectors from an R2 vector space and gives me new vectors in R2. This is the function of m. And so right here you can see it takes that green vector here and gives me this new green vector. Takes that black vector and gives me that black vector. Takes the yellow vector and gives me that yellow vector. And so on. And so, as you can see here, it takes a circle, the circle of vectors, these are the vectors that have unit 1, and gives me an ellipse of new vectors. Now, you can always find an inverse to this particular map. I can always find an inverse, which I'm going to call m-1, because I take the black here, and I can go back from that black vector to find the pre-image of the black vector. Similarly, from the yellow, I can find the pre-image of the yellow. From the green, I can find the pre-image of the green, and so on. So you can see that there is a one-to-one map between every vector and its image. Now let's look at another example. In this example, I have a different form for the matrix. M has the form 1, 2, 2, 4. So let's see what happens to the vectors here. It takes this black vector and gives me this new vector. This green vector, it's somewhere here. So it takes all these vectors and just gives me a line instead of an ellipse. It's missing one direction. Nothing is mapped to vectors here. And so I'm not able to go back. There's no m-1. There's m, but there's no inverse. m-1 does not exist. And in fact, you can always find many vectors here. In particular, you're going to find that this vector here is mapped to the 0 vector. So I can take that vector, it's going to go to the 0 vector. And so matrices are not always invertible. An invertible matrix will transform a circle to an ellipse. A non-invertible matrix will transform a circle to a line. There are 3 statements in the website. The 3 statements, you have the proof for them. I don't really ask you to memorize the proof or anything, but I want you to read the proof and try to understand it. And I want you to understand that statements really well. The first statement is if I have a map, a linear map, from Rn to Rn, T is injective, it's 1 to 1, if and only if its kernel is equal to 0. So the vectors that are mapped to the 0 vector is only 1, which is the 0 vector. The second statement is that an invertible map, or T is invertible, if and only if kernel of T is equal to 0. So all I want to know, if I want to know about a matrix, if it's invertible or not, if I can know something about its kernel, which vectors it takes to 0, if the kernel contains only one vector, then T is invertible. And the final statement, T is invertible if and only if the n vectors forming the square matrix of T are linearly independent. So let's remember the last matrix that we had here. If the rows are linearly independent, then the matrix is invertible. Here the rows are linearly dependent. And so the matrix is, in this case, is not invertible. I cannot find an inverse. And we showed that in the previous slide. And so we're going to use that last statement to try and identify whether a matrix is invertible or not. So basically, the one thing we want to know is whether those rows of the matrix are linearly dependent or not. If they're linearly dependent, then I cannot find an inverse. If they're not, then I can find an inverse. And so the tool that I use to identify whether a matrix is invertible or not is the determinant. The determinant is a function that gives me 0 when the rows are linearly dependent. So if I have a matrix M in R2, it's a 2 by 2 matrix, and it has components A1, A2, B1, B2, the determinant of M is defined as the term A1, B2 minus A2, B1. And you can really easily show that the determinant of M is equal to 0 if and only if A1, A2, and B1, B2 are linearly dependent. And so if they're linearly dependent, if they depend on each other linearly, then the matrix is not invertible, and in that case the determinant is 0. This determinant has also another function. Its function is, geometrically, it gives me the area of the parallelogram that formed when I take E1, x1 is equal to m E1, and x2 is equal to m E2. So this is transformed into this parallelogram. The area is equal to the determinant of M. So the determinant of M tells me something about how areas change when I apply this linear map between vector spaces. Some properties, you can easily show them just using components. The determinant of Nm is equal to the determinant of N multiplied by the determinant of M. If I multiply the matrix M by a number alpha, it's equal to alpha squared the determinant of M, and the determinant of I is equal to 1, where I is the identity matrix. For a 3 by 3 matrix, the determinant of M is defined as follows. If I have those 3 rows of the matrix, each row I'm going to designate it as a vector, the vector A, the vector B, and the vector C. The determinant of M is defined as the A dot B cross C, which is the triple product of the rows. And if you remember when we studied the Euclidean vector spaces, especially when you studied the cross product, the triple product A dot B cross C is equal to 0 if and only if the rows are linearly independent, which means this is true if and only if the matrix M cannot be inverted, which if and only if the determinant of M is equal to 0. The determinant of M gives me a geometric measure. If I have the 3 vectors E1, E2, and E3, and once I multiply the space by M, then I get x1, which is equal to m E1, x2, which is equal to m E2, x3, which is equal to m E3. Then in that case, the determinant of M is equal to ME1 dot ME2 cross ME3, which is the new volume after transformation. Another very important property of M, or the determinant of M, is the following. If I have three vectors that are linearly independent, U, V, W, we know that this volume is equal to U dot V cross W. When I multiply these vectors by M, I get MU, MV, and then MW. And so the new volume here is equal to MU dot MV cross MW, the triple product, as we studied in the linear vector spaces. The original volume is U dot V cross W. So the determinant of M is equal to the ratio of the volumes. I'm going to call this V2, and this is V1. The determinant of M is equal to V2 divided by V1. Some properties of the determinant. Again, for M being a 3 by 3 matrix, for any two matrices n and m, for any alpha in R, the determinant of nm is equal to the determinant of n multiplied by the determinant of m, and the determinant of alpha m is equal to alpha cubed multiplied by the determinant of m, and the determinant of the identity matrix is equal to 1. The last basic definition that I want to talk about in linear maps between vector spaces is the eigenvalues and eigenvectors, and I'm going to study that by just looking at examples. The matrix M that takes vectors in R2 and give me vectors in R2 and with whose components are 1, 2, 2, 1 does the following. Takes that green vector and gives me this new green vector. And as you can see, this new green vector can have a different direction. It was originally vertical and now it's oriented, and it originally had a length of 1 and now has a different length. And so every vector changes its length, or it could change its length, and it could change its direction. The eigenvector is a vector that does not change its direction. And you can see here, this black vector did not change its direction. I'm going to call this EV1, and this is MEV1. As you can see, this is in same direction as EV1. And I have another vector here, EV2. Again, this is MEV2. It's in same direction. And so they are special vectors. These are called eigenvectors. These are the vectors that after transformation by the matrix do not change their direction. If I have the basic definition, if I have a matrix M from Rn to Rn, a real number, lambda, is called an eigenvalue if there exists a vector and this vector is not 0, such that MP is equal to lambda P. In this case, P is called an eigenvector of M associated with the eigenvalue lambda. As you can see here, the vector P does not change its direction, it just gets magnified or it gets shrunk by a factor lambda. Notice the following. Any multiplier of an eigenvector is an eigenvector, because if MP is lambda P, then M alpha P is equal to lambda alpha P as well. So alpha P is an eigenvector of M, which basically says if I have a vector here, let's call it P, then MP is equal to lambda P. If I actually choose the vector to 2P, Then 2p is also an eigenvector. And I'm going to get here m2p, which is equal to lambda 2p. And so any multiplier of an eigenvector is also an eigenvector, and that's why we usually try to normalize an eigenvector after we find it. Also, the addition of two eigenvectors gives me another eigenvector. That's because of the linearity of the matrix operation. So if I have one eigenvector mp equal to lambda p and another eigenvector mq equal to lambda q, then m alpha p plus beta q, because of the linearity of the matrix, it's equal to alpha mp plus beta mq, which is equal to lambda because mp is p is an eigenvector, so this is equal to alpha p. mq is an eigenvector, so this is equal to beta q, and so alpha p plus beta q is also an eigenvector of m. So now, as we understood what an eigenvector and eigenvalue is, we would like to know how can I find an eigenvalue. And to find an eigenvalue, it's a simple computation. I would like to know what is the vector p, that when I multiply by m, I get lambda p, which is basically as if I'm saying m minus lambda, the matrix I, multiplied by p, is equal to 0, which means m minus lambda I is not invertible. Not invertible, right away, the tool that I have is the determinant, so set the determinant of m minus lambda I equals 0, and from here find lambda. And after you find lambda, you find corresponding p. And we'll show you using examples. So I have a few examples on the website, and here's it's section 2.2.6. So for example, if I have the matrix M and I'd like to find its eigenvalues and eigenvectors, I set the determinant of M minus lambda I equal to 0. So the determinant of the matrix M minus lambda I equal to 0. So the determinant of this is equal to 0. You can calculate the determinant by the triple product of the three vectors. So you get 1 minus lambda cubed minus 1 minus lambda equals 0. So this is the determinant of M minus lambda I, from which you get this cubic function of lambda. This is the cubic. Then by simplification, you get this function of lambda. From here, you have lambda has either 0, 2, or 1. Can be have one of those three values. So there are three possible eigenvalues, 0, 1, or 2. Now to find the corresponding eigenvector, we're going to show you how to find it for the third eigenvalue, lambda 3 equal 2. So I'm looking for the eigenvector 3, such that when I multiply m by the eigenvector 3, I get 2 multiplied by the eigenvector 3. So I'm going to solve the equation. When I multiply m by the three components of the eigenvector, I get 2 multiplied by the three components of the eigenvector. And so in the first equation, I have 1 multiplied by the first component plus 1 multiplied by the second component equal to 2 multiplied by the first component. So I get this equation, which tells me that the second component minus the first component is equal to 0. And from the second equation, I get the first component minus the second component is equal to 0. And from the third equation, I get that the third component is equal to 0. So using these two equations, they're actually, basically, they are the same equation, which tells me that both components, the first and the second component, are equal. And so because both the components are equal, I can set them to anything. So I can set that the eigenvalue, the eigenvector, the third, is equal to, I can set it alpha 0. But then I'd like to normalize it, because normalizing, I'd like to deal with unit vectors, and when I normalize it, it will be equal to 1 over root 2, 1 over root 2, 0. this is equal to the normalized norm of eigenvector 3, in this case, is equal to 1. And you can see other examples on the website in the section Examples and Problems.